So we're just going to go through the answers to the questions from the Binomial Basics that was on Schoolbox in the files section. So I'm going to start with question 5, but I'm going to go back up to question 1. So if x is a random variable that's distributed as a binomial variable with Bernoulli probability 0.1 and number of trials 6, find the probability that x equals 4. So basically, they're saying x is a binomial and it's got the number of trials is 6 and the Bernoulli probability is 0.1. So that's what they're saying in that sentence there. You have to find the probability that x equals 4. X is exactly 4. Now we know that the probability that x is exactly 4 for the binomial here in this situation is 6C4, because 6 is the number of trials, and the probability of success to the power of 4 and the probability of failure to the power of 2. If you wanted to, you could write down the fact that the situation here is describing 0.1 plus 0.9 to the power of 6. And you're expanding it out and you're just picking the term which has k equals 4 as such in there. So the probability that x equals to 4, you need to get on your calculator and you need to work out what that is. So 6 shift divided by 4, which is 6C4, times 0.1 to the power of 4 times 0.9 to the power of 2, and 243 on 200,000 is the answer, which is 0.001215. Not much probability that you'll get exactly 4 right. Now, this makes sense if you go by the multiple choice idea. If your chance of success is 0.1, it's like there's 10 options in the multiple choice question. A, B, C, D, E, F, G, H, I, J. There's 10 options. So if you guess, you've got a 1 in 10 chance of getting it. So that's where your 0.1 might come from. And they're saying if you have 6 such questions, each with 10 options, 6 multi-questions that are A to J, what's the chance of getting 4 right? Well, I don't reckon there's much chance of getting 4 right. There's not much chance of getting 1 right, is there? You know, 0.1 of getting 1 right. How many ways to get 4 right? And that means to get exactly 4 right, you're getting 2 wrong, because we're just going for exactly 4. So I think that that's a fair call. The standard deviation. Now, you know the formulas that the expected value is NP and the variance of x is NPQ. So I can work out the variance first of all, because that's N, 6 trials, times P, which is 0.1, times my Q is always referring to 1 minus P. So that's the variance, and we want to square root that to get the standard deviation. So we've got 6 times 0.1 times 0.9. So we've got 0.54, and we square root that, and we get 0.7348. So the square root of the variance is equal to 0.7348. That's what the standard deviation is. All right, so I said we'd start with that one, but we'd move back to question 1. So I just will find that on my hopefully that's taking me back to question 1. All right. Question 1, find the probability that x equals 2 if the probability that x equals x is that. It's just another way of asking a binomial question. It's just expressed that way. So basically, you just need to put a 2 in here, a 2 in here, and a 2 in there. So you're finding 5c2 and a quarter to the power of 2 and 3/4 to the power of 3. So you just need to put that in the calculator once more. So 5 shift divided by 2, that's 5c2, times a quarter to the power of 2 times 3/4 to the power of 3. And I get 135 on 512, which is better than the decimal. So I'm going to leave that as 135 on 512 instead of a big long decimal. Complete. If x is a random variable distributed as a binomial with 6 Bernoulli trials, each with a probability of success of 1/5, then the probability that x equals x is 6cx, and then it's 1/5 to the x, and 4/5, because that's the probability of failure, to the 6 minus x. What do the parameters stand for in each of the following? All right, N stands for the number of Bernoulli trials, and P stands for the success, probability of success. Mean, variance, standard deviation squared for this. This is binomial distribution. This is a normal distribution. This is a discrete random variable. This is a continuous random variable. A test contains 12 multiple choice questions, each with 5 possibilities, A, B, C, D, E. Tarquin guesses all 12 questions. Tarquin's interested in finding out the probability that his result will be exactly 50%. What is x in this situation? So x is the number of questions that he guesses correctly. So he can guess 0, 1, 2, 3. There's 12. So x can be anything from 0 up to 12. How many questions he guesses correctly. Complete for this situation, x squiggle, well, it's a binomially distributed random variable with 12 Bernoulli trials, each with a 1/5 chance of success. Find the probability that Tarquin's result is 50%. So find the probability that he guesses exactly 6 of the 12 questions. So 12C6, 1/5 to the 6th, 4/5 to the 6th. He guessed exactly 6 questions. So we pop that in the calculator, and we've got to the power of 6 times to the power of 6 equals, and it's a big long decimal, 0.0155 roughly. So that's the chance that he'll get half of them right. Not even, well, it's about 1.5% chance if you convert that to a percentage. So it's not very high as expected. Okay, find the probability. It says that Tarquin gets at least 4 questions correct. Now, at least 4 questions means that he could get 4 questions correct, 5, 6, 7, 8, 9, 10, 11, 12. I don't want to work all them out. I'd rather work 1 minus the opposite. Whenever I see at least, I think do 1 minus the opposite. So instead of at least 4 questions, I'm going to do find the probability of none, 1, 2, or 3, and subtract that away from 1. So I'll write that up here. 1 minus the probability that x equals 1 or 2, 0, or 1 or 2 or 3. So I'm going to have to work that for each of these, right? Instead of a 6, I'll have to put a 0, a 1, a 2, or a 3 in here, right? So it's 1 minus, and it's 12C0, 1/5 to the 0, 4/5 to the 12, and 12C1, 1/5 to the 1, and 4/5 to the 11th, and 12C2, 1/5 to the 2, and 4/5 to the 10, and 12C3, 1/5 to the 3, and 4/5 to the 9. Now I add up all those, subtract that from 1, and that will give me the answer. 1 minus 12 times 0.2, just typing it in the calculator. Hope I don't make an error here, but you can do what you do and see if we get the same. I'm a bit lost in what I'm doing now. So I'll just finish up here and hope that I've typed the right thing in. Well, I think if this is correct, the answer is 0.20543. Chance, the probability that Tarquin gets at least 4 questions correct is 0.2. So that means getting all those other ones. And it sort of makes sense because it doesn't have much chance of getting some of the higher numbers correct, does it? So I feel like that's okay, but I might have pressed a wrong button there somewhere along the track. That was question 3. Let's have a look at question 4. The mean find the mean and variance of x if it's that binomial distribution. So that's n, that's p, and q will be 0.7, right? So the mean should be equal, the expected value should be equal to n times p, which is 2.4, and the variance should be equal to npq so that should be equal to 8 times 0.3 times 0.7 should be equal to 1.68. Then you could square root that if you want the standard deviation. Finally, their formulas you should know and be able to work with. Finally, we'll have a look at the last question, which was, it says, now for a binomial probability joke. So maybe I can increase the size of that so we can see it a bit better on the page. Suppose a stand-up comedian plans to give a total of n equals 5 jokes in an entire 2-hour performance. Call a joke a success if at least one audience member laughs. If no audience member laughs, the joke is a failure. Assume that all the jokes are equally funny, with P equals the probability of success, which is 0.2. Let X be the random variable that denotes the number of jokes out of the total 5 were successes. Precisely state the distribution of X, giving the values of any parameters necessary. So they're just saying, write down the fact that X is a binomial. How many jokes does he give? He plans to give 5 jokes, and the chance of success is 0.2. So that's our binomial. Calculate the probability that the whole night is a failure. So the probability of no laughs. So that's the probability that 0, X is 0, the number of jokes out of the 5 is 0. So if I can just write it here, that would be 5C0, 0.2 to the 0, 0.8 to the 5. So I pop that in the calculator. Of course, that's 1 and that's 1. So it's just 0.8 to the power of 5, which is 0.32768. 0.32768. Nearly a third of a chance this whole night's going to be a failure. Calculate the probability that the comedian tells at least 4 successful jokes. Well, since there's only 5, I could work out 4 and 5. That would be easier than 1 minus the opposite. So I'm going to do 5C4, 0.2 to the 4, 0.8 to the 1, plus 5C5, 0.2 to the 5, 0.8 to the 0. So that's 4 and 5, so that's at least 4. And I'll add those up. So 5C4 times 0.2 to the power of 4 times 0.8 plus, now that's 1 and that's 1. So I just need 0.2 to the power of 5. And I get 21 on 3125. 0.00672. 0.00672. It's a 0.7 chance of a success, not even a percent, 0.7% chance, not even a 1% chance of 4 successful jokes through the night. Calculate the expected number of successful jokes. We know the expected value of X for a binomially distributed random variable is n times P. So it's 5 times the 0.2. So we're expecting there to be 1 successful joke in the evening. All right, so now I just got to find the camera and press